So this section of the chapter talks about energy. Energy is a major component of our universe. Energy is a little harder to understand than matter. Matter's easy. If it takes up space, if it has mass, it's matter. What is energy? Well, energy is kind of the rest of the stuff. One definition of energy is the capacity to do work, the ability to do work. Well, then, what is work? Because some of these science terms are a little different than how we use these same words in our everyday lives. What is work? Work is defined as the result of a force acting on a distance. So you may go to work and sit in a chair and think about things, right? And you're getting paid for that, that's work. But according to science, that's not work. According to science, picking up this pen is work because I'm exerting a force across a distance. Kicking a rock down the sidewalk is work. Walking is work. So we use these little words a little differently. So that's what work is. So energy is the capacity to move something over a distance or apply a force across a distance. The behavior of matter is driven by energy, and that's why these two things are related. Why does matter do what it does? It's because of energy. Energy drives it. So we have to understand what energy is and some things about it so we can understand chemistry. Oops, skipped a slide. We talked about how matter is conserved. When you have a chemical reaction, the mass of the reactants is equal to the mass of the products. Energy is also conserved. So this is called the law of conservation of energy. Energy is neither created nor destroyed. The total amount of energy in the universe is constant. So you can't just generate energy out of nothing. You can change energy from one form to another, though. So you can take chemical energy stored in gasoline and change that into kinetic energy of your car moving down the road. That's just changing from one form to another. And there are some forms of energy that are not immediately obvious to us. Energy can also be transferred from one object to another, but you can't create energy out of nothing, and it doesn't just disappear. Now, you can take a useful form of energy and dissipate it into a non-useful form of energy, but the energy of the universe is constant. So there are different forms of energy, and energy can be transformed from one form to another. And so these are the sorts of energy that we'll be talking about in chemistry. Kinetic energy is one type of energy. Let's see, I need to get something to write with here. Long, annoying pause here. Come on. Oh, fine, I'll use it that way. So kinetic energy. Kinetic energy is energy of motion. So when something is moving, it has kinetic energy. There's also potential energy. That's energy associated with position or with composition. So here's my Bic pen. When I hold it high above the ground, it has potential energy. It has the potential to do work. It has the capacity to do work due to its position. When I let go of it, gravity acts on it and it falls to the ground. As it falls, its velocity, its speed increases, and it has kinetic energy. The potential energy that it has decreases as it gets closer and closer to the floor. But it's speeding up as it gets closer to the floor, and its kinetic energy is getting greater. Then it hits the floor, and now it's got much less potential energy, and it's got almost zero kinetic energy, what happened to the energy that it had up here? It gets dissipated as heat. You're like, what? That didn't get hot? Pen hitting the floor? Well, it's a very small amount. When you have two large objects that collide with each other and stop their motion, there's heat that's generated. Heat is often a not very useful form of energy. We sometimes give the example of someone swinging on a swing. And you swing up, and when you come to the top of your swing, you stop momentarily. And then when you come back down at the bottom of your swing, you're going the fastest, and as you go back up the other side, you start to slow down. And that's, next, I don't know how often you swing. We do have a swing set in our backyard. When you're swinging, you're like, hey, I'm transforming. Potential energy, kinetic energy, potential energy, kinetic energy. Yeah, you're not going to do that, are you? Then we have electrical energy. Electrical energy is energy associated with flow of electrical charge. So that's a very useful thing. The electric current in the outlets, that's electrical energy. Then we have thermal energy. Thermal energy is the energy associated with random motions of atoms and molecules. We talked about the 3 states of matter and how even solid objects are not perfectly stationary. The individual particles are moving, they're vibrating and oscillating. If you add heat to them, if you heat them up, they start to move more, and that's their thermal energy. And then we have chemical energy. Chemical energy is a form of potential energy. It's associated with positions of particles that compose a chemical system. It has to do with the relationships between atoms in a compound or an element. Those relationships have potential energy, and we call that chemical energy. Any questions about forms of energy? Yes?
Where does inertia tie in?
Where does inertia tie in? An object in motion tends to remain in motion. An object at rest tends to remain at rest. See, this is going into physics. And I'm rusty on my physics. You're rusty on your chemistry. That's okay. That's why I'm up here and you're sitting there. Inertia, and the friction plays a part in that too.
It's a form of energy, though, correct?
Is inertia a form of energy? I'm not sure about that. I don't know. I'd have to look that up. That would be a good thing to look up. But if you've got a boulder, or I don't know, maybe the couch sitting there, and you need to move it. Initially, you have to push a lot harder to get it started, right? And then once it's moving, it doesn't take as much energy to keep it moving. And that's inertia. That also has to do with static friction versus kinetic friction. And static friction tends to be greater than kinetic friction. Once you overcome the static friction, then it's easier to keep it moving. So there is some interplay between those things. And yeah, I haven't had physics since my sophomore year in college, so I liked it, but I only remember what I need to remember, right? But that would be a great thing to look up. So energy is something that can be measured, so we need units for it. So the SI unit of energy is the joule. That's a funny word. Pretty sure it's French. It's pronounced joule, like a jewel in a crown, and the abbreviation is a capital J. Another unit of energy is the calorie, and you've probably heard of that one. So we talk about how many calories are in our food. That refers to how much energy is in your food. A calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. We should know the relationship between the calorie and the joule. A calorie is larger. A calorie equals 4.184 joules. And then this calorie that we were just talking about is not the same as the calories in your food. The calories in your food are nutritional or dietary calories, and they are calorie with a capital C. And they are even bigger than a regular calorie. So we've got calories with a lowercase c, and the abbreviation is just CAL, no period. And then we have the nutritional calorie, capital C, capital CAL is the abbreviation. So when they say that, the soda has 260 calories or whatever, they're talking about these nutritional calories. And that is equivalent to 1,000 calories. So essentially, the big calorie, the nutritional calorie, is a kilocalorie. So if a soda has 260 calories, it's got that much energy in it. So 260,000, it could raise the temperature of 260,000 grams of water by 1 degree Celsius. It's a lot of energy. And your body takes that energy, and how does food have energy? It's potential energy, it's chemical energy in the food, in the molecules. Your body does chemical reactions on the food which generate energy from it. And then the electric company uses kilowatt hours as their unit of energy. And we're not going to do much with kilowatt hours. But we do need to understand joules and calories, both kinds. Here's the relationships between these units. And calorie and joule are both metric units, and so we can use the metric prefixes with them. And so we can talk about kilojoules or kilocalories. That's usually the only prefix we use. We don't talk about millicalories or anything, but we will see kilocalories. So that's a useful table to refer to for conversion factors. So let's use these. We've learned how to do dimensional analysis and convert units. Now we just have some new units to play with. So the complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? Okay, so again, we're going to pick out any numbers that are in here with their units. So we've got 512 kilocalories of heat. We're probably going to need that. And then we need to figure out what is the question, how many kilojoules? So this comes down to being a unit conversion problem. So we're starting with, we're given 512 calories. The question is, how many kilojoules? Well, you can go to the table on the previous page. Is there a relationship given between calories and kilojoules? No, there isn't. Well, is there a relationship between calories and joules? Yeah. So we could convert calories to joules. Can we convert joules to kilocalories? Yeah, because we could convert snickerdoodles to kilo snickerdoodles, right? A kilo snickerdoodle. This is 1,000 snickerdoodles. That would give you a stomach ache. Okay, so we find our path. The path, again, based on factors that we know or have access to. And so then we just start writing our equation. 512 kilocalories. Our path has 2 arrows, so we have 2 conversion factors. And the units in the path become the units on top of our equation. Calories to joules to kilocalories. Calories to joules to kilocalories. Sorry. Calories to joules to kilojoules. Calories to joules to kilojoules. Maybe I need to repeat that a few more times. I can't even read my own writing. So we put the units on the top. Then we take this unit and it comes down here because we don't want calories in our final answer. We want those to cancel out. And we bring joules down over here because we want the joules to cancel out. Remember this? Now we need relationships between these two. Well, kilojoules to joules is the easiest one. We've got kilo up here. What does kilo mean? 10 to the third. So up here we have the abbreviation. We're going to put what it means on the other side of the line. So that one's good. And then joules to calories. Well, we look that up in the table and we find that 1 calorie is 4.184 joules. And now we're ready to do the math. We've got 512 times 4.184 divided by 1 EE3. And how many significant figures should our answer have? It should have 3. Our initial value was 3. This one is not exact, but it has 4. This guy's exact, so we don't have to worry about it. So the calculator says 2.1422, and then I'm going to round that 2.14 kilojoules. And there's my answer. Any questions?